Okay, so we want to talk today about Leibnizian notation for differentiation. We've just learned the start of differentiation, okay? And we know the fact that if you've got some function, if we call it fx, let's do an example, equals, let's do 3x squared, okay? How do we find f dashed of x? Please, Maya. You're going to have to shout.
It's the n, wait, what? Oh.
Yeah, it's the,
N
yeah.
of x.
It's so, you're right.
If
If f of x equals x to the n, then f dashed of x equals n to the n minus 1, yes. Yep, which gives you what?
6x.
3 times 2x, which is 6x, is correct, okay? This is commonly referred to as Newtonian notation. It isn't. This is notation invented by Lagrange. Lagrange used this functional notation, f dashed of x. You will later learn about f double dashed of x, which is to say the derivative of the derivative and higher, more derivatives, okay? Actually, the reason why Leibnizian notation is better is because is so widely used. All integration is written in Leibnizian notation, and the reason why is because it's actually a bit more subtle. We call it y equals 3x squared. Okay. Now I'm going to draw that graph briefly, just a little section of it. Yeah. Let's call this far out. Let's call this point here x comma 3x squared. Okay. Now, previously I have given you the horizontal change being what, Archie?
H.
Yes, h is correct. The horizontal change was h, the small, and which we then did what to h? We took the limit as?
As H approaches 0.
That's right. We're not going to do that now. We're going to make a new symbol. Okay, don't freak out. We're going to choose a delta x. Okay? The horizontal change is a delta x. That's a small triangle. I know it's weird. The uppercase Greek letter delta is just a triangle. Okay, the letter D basically. But we're using a small triangle D. That's a delta x. Okay? Which is obviously causing a change in y, which we're going to call what?
Delta f of x.
Delta y. Yeah? Yeah, you with me? Change of, so we're used to this as x f of x. So this point here is x plus delta x, comma, y plus delta y. Yeah, those are the two coordinates of that point. Yeah? We'll do it with the actual function in a second. This is the point P, and this is the point Q. Yeah? Well, let's not do it as 3x squared. Let's just do x comma y. Let's do it as x comma y for now. X comma y, change in x, change in y. X plus delta x plus delta y. What is the derivative? What is the gradient of the secant PQ? Let's start with the gradient of the secant PQ. What do you think? Yes?
Delta y on delta x.
That's really easy, isn't it? It's obviously the change in y over the change of x. It's really nicely written, yeah? Now, do you agree that the gradient of the tangent at P is obviously what? Hands up. Some of you use this as your sitting down fact. How do you find the gradient of a tangent? How do you find a tangent? No. How do you find a tangent? Sorry? If the limit as q approaches P, yeah? So in this case, it's going to be the limit of your change in y over your change in x as what? As what?
Delta x approaches 0.
As delta x approaches 0. Okay, now I need a little bit more notation, and I've left myself not enough space here. Can we just ignore this one for ignore this example? Let's come back up here. Yeah. So delta y over delta x is a change in y over a change in x. You'll hear people use a delta a lot in life. A delta generally means a change. A delta is a change. Calculus, by the way, if you want to know a four-word summary for what calculus is, it is the study of change. You are studying how some variables are changing in relation to other variables. Yeah, that's what calculus is. So that is what delta x over delta y is. This is the gradient of a secant. Delta y over delta x. Now that is now a not lowercase at all. A lowercase Greek delta over a lowercase Greek delta x, delta y over delta x. Sorry for the interruption. A delta y, a lowercase Greek delta over a lowercase Greek delta x, delta y over delta x is a small change in y over a small change in x. Okay?
What the hell?
Now, this is a new notation that's about to happen now. Okay? As delta y, so let's call it the limit as delta y approaches 0 of delta y is called dy. Okay? Now I know that seems like a weird thing to say, okay? But dy, okay, dy over dx is an infinitesimal change in y over a what? What do you guess? Take a guess.
Infinitesimal change in x.
An infinitesimal change in x. So what they're saying is it's the gradient, it's the change in y over the change of x, it's the delta y over delta x as they become 0. So it's not quite wrong to say, it sort of is wrong, but it's not quite wrong to say that dy over dx is kind of 0 over 0. Yeah? As in the infinitesimal change in y is technically speaking 0. And the infinitesimal change in x is technically speaking 0. It's just sometimes that 0 over 0 can be in a stable ratio, and you've seen that. Yeah? You were happy enough to agree that the limit as h approaches 0 of h over h is what, Alex? 1. You were happy enough to agree that while 0 over 0 is not defined, that the limit as h approaches 0 of h over h is fair enough 1. Yeah? So I'm saying, for that reason, that infinitesimal changes in y can be in a stable ratio with infinitesimal changes in x. That might be 0, it might be infinite, it might not be finite. But if it is finite, we can find them what they are. They can find what they are. Oscar.
The symbol there, that's delta, right? I just can't really see it.
This is a delta. This is a capital delta, but a small one. A capital delta should really be...
What's the one beneath it?
Sorry, just a minute. Okay. So this is a capital delta, but it's actually a small one. I don't know why. We've got two versions. The capital delta should be like double height, but we've given you a small capital delta. This is a lowercase delta. Just, I want to teach you a few things here. One, do not write this. Some of you like a sort of, you write in a slightly elvish way or whatever, like you like a little, that there is a different mathematical symbol. That's a del. It means a partial, it's a part, like del y, del on del x of y is a partial derivative of x in the direction y. I think, I forget, it's about three-dimensional, it's most commonly used in three-dimensional calculus, okay? So don't just decide that you don't need the little squiggle, okay? That's a del. You actually want to properly write a full delta, yeah? With a little curl, you usually start at the top and you curl it around. That's what a delta looks like, yeah? So delta y on delta x, to return to your idea, delta y is not an infinitesimal. Delta y is a small change. Yeah, you can imagine that small changes, we're now approaching the true gradient. Yeah, But when you take the limit as that approaches 0, you get a dy over dx, which is an infinitesimal change. You're looking at the ratio of two infinitesimal things to get the stable gradient. So if we go back to, instead of f(x) equals 3x squared, you do y equals 3x squared. That is an expression instead of f of x equals y equals 3x squared. My next line to find the derivative is dy dx. Do not say dy over dx, although it sort of is. It is pronounced as dy dx, or the derivative of y with respect to x. The letters WRT are almost universal in maths. They mean with respect to the derivative of y with respect to x, as in, how does y change as x changes? What is the rate of change of y as x changes is what that's asking. Okay? dy dx is what expression in this case, Henry?
dx, 3x squared.
No. Y equals 3x squared.
6x?
dy dx is,
6x.
it's the derivative. Yeah? Now, what's subtle about this is that you can, over here, back in Leibnizian notation, you've got f of x and f dash of x. It's all xxx, right? There's x and what you did to it. Over here, you're relating two different variables, a y and an x, and this is extremely useful in a lot of calculus that we're going to do, and it's especially useful in integration because this is very hard to notate in integration, which is the next thing we're going to do. Okay? This here is Leibnizian notation. Just so you know, Newtonian notation. Does anybody know Newtonian notation? Yeah?
Oh, no.
Displacement in Newtonian notation is x, like that's the position of the particle. You differentiate it to get velocity, as in the rate of change of where you are over time is your velocity, yeah? It's your speed. Velocity. It's written as x dot, which you can't really see on my thing because of the reflection, but whatever. It's x dot, and the acceleration, which is taken to be the rate of change of your velocity. You with me? As you change velocity, you accelerate, yeah? Is x dot dot. You with me? This here is the notation that Newton actually used, okay? Used a bit in Extension 1, Extension 2. Actually, my Year 12 Extension 2 class are about to start with this. My Year 12 Extension, the Extension 1 class, who Miss Whiteley just tried to phone us a moment ago, they similarly have the same, that they're about to start that stuff, yeah? Okay, that's actually Newtonian notation. Newton used this notation. Leibniz used this notation, and we're going to use this a lot more than over here. This functional notation was used by Lagrange in France. Sort of French, German, English. Okay? Different notations. Okay? Now, if you are of a mind to like, Mr. Horton says a lot of things that don't mean anything, and I just don't really want to pay attention, and I'd rather just learn things that will get me marks and not understand anything, and because I'm not going to do maths at university. If all you learned is that the derivative of y is dy dx, that's enough. Yeah? This is like f of x equals f dash of x equals y equals dy dx equals. If that's all you want to learn, then who am I to stop you from going out into the world without proper understanding of calculus? Now, one thing I will say is the double derivative is a little bit more subtle. We haven't got to that. We will get to that, I think, right at the end of this chapter. We might be doing double derivatives, as in the derivative of the derivative. Another thing I want to kick out of your minds is that I am differentiating to get the derivative. The process of obtaining a derivative is called differentiating. I'm differentiating to get the derivative. This is what it is not, but which many of you will say, even though I tell you what it's not. You are not deriving to get the derivative. I know that seems like it should be. I know that word seems like it's related to the word derive, which it is. The derivative is the outcome of the process of differentiation. You differentiate to get the derivative, okay? You don't derive to get the derivative. Deriving is a different process. Like you derive the quadratic formula from ax squared plus bx plus c equals 0, right? Deriving is a sort of process of going from like some premise to some conclusion, yeah? That's how you derive a formula based on some facts that you know. This is differentiating. It's not deriving. Was there a question?
Yes.
Yes.
Don't do double differentiation.
In this chapter?
No.
When do we do it? In year 12. I get a bit confused sometimes.
I think the last thing with this chapter is continuity.
Okay, awesome. Okay, so for those of you who weren't here today, that is a little summary of that next skill. I'm trying to think if there's... that'll do for this. That'll do for 9D. Okay?
Would this also be sent to me?
9D, off you go.
For the campus.